This is Sadhna, and today I will be explaining the applications of Automata in search engines. Now, we will be mainly looking at small subtopics inside that, which is keyword matching, spam filtering, auto completion, spell check and correction, and natural language processing. Now, before we delve into all this, what exactly are search engines? Search engine is a software system that is designed to help users to find information on the internet. Now, we've been using search engines all while, and they can be Google, Bing, Yahoo, and all such things, etc. Now, what exactly are finite automata doing in that? What do we do in search engines? We search. So, search engines use finite automata to find keywords and query to find relevant results for the user. So, we know that whenever I type something, say for an example over here, I've typed what is the search engine, I know that I'm going to get relevant results, results where websites are going to say something related to search engines, right? How exactly does it know that it has to give something related to search engine? That is using a keyword. Now here the search engine is a keyword. The finite automata will figure out that a keyword search engine has been used, and then it will use that to find relevant results related to this search engine in the query that we have given. That is keyword matching. So what is spam filtering then? Keyword matching, spam filtering also uses keyword matching in one such case. Here it tells us that whenever I give a query, it filters out and gives me the most relevant ones. So here you can see that there is a certain order in which the websites are given. The orders in which these websites are given has certain relevance. This is the most relevant one, and this is the least relevant one kind of thing. Also, the search engine will use finite automators to assign certain web tags, and it will help us to filter out spam results. We know that certain websites can be malicious, right? So how exactly this finite automata finds that? It assigns certain tags. Say for an example, it also uses rejects patterns, and finite automata will be able to detect this scam domain name. So it will be like, okay, I have received this domain name, so I have to stop it. Is what it will think. Similarly, it also has certain patterns, and it will be able to recognize all these things like a link shortener that is malicious for us, or else it can also take us to a very bad site. So finite automata also prevents that. Then we go to autocomplete. Now, without autocomplete, our lives would become really, really very difficult. So when we are texting or when we are typing in Google search itself, we know that as we type, it gives us certain recommendations, and also it will let us complete what we are trying to do. So here is exactly a small scenario of what exactly would happen when we are typing. So say for an example, I want to type the word cart. So I start typing C, and then I'm in state Q2 now, and then I type in and I go from Q2 to Q3, I give A. So when I come to Q3, it will suggest me car as well as it will suggest me cat. And when I type T, Q6 accepted state. Similarly, when I type R, Q4 accepted state. And okay, so now I move on. I write CAR, and it will again suggest me T or E for both car and cart. So either T or E, both of them, it will be accepted. So this is how auto completion works. And all these need to be pre-computed based on the English dictionary. But as soon as that is done, it is a very easy process. Similarly, we have spell checking and error and correction. So now sometimes we might type really, really very fast in the search engine, right? So these search engines are also capable of spell checking and correcting the spelling mistakes in our query. Now, when it corrects all these spelling mistakes, the search engine can understand the query much more better. So what I did was I typed what as a search engine. So here I is wrong, and here this U is wrong, needs to be replaced by I. This I needs to be replaced by E. And we can see that it is actually checking the spelling and telling us, okay, are you trying to type this? Is what it's trying to tell us. That is very smart of it, right? So how exactly does it do that? Let's look into something called lexicon based matching. So here what we are going to do here is here we have APEEX. Seems to be very complicated, but let's take an example. Say for an example, I intend to type apple, but by mistake I type APPL. Now, what will happen is, see, say for an example, even in Word documents, when you type, if there is a error in the word, we know that it will indicate by changing it to red. There'll be certain red color lines below it, and then you can click on it and change it, right? So here also it is pre-computed. So when I type A, goes to Q2. Similarly, I give P, goes to state Q3, and then after that, if I type E, A is a correct word, it will be accepted in the dictionary. Similarly, apex is also there and accepted in the Q5 state. But let's say I give ABPL, it is not a meaningful word, not in the dictionary, so will not be it will not be accepted, and it is an error. Then we look into the Levenshian automata. So over here, it is a special type of automata used for approximate string matching, particularly for identifying strings that are within a certain edit distance. Now, this seems to be very complicated, but the main idea over here is if there is a certain word, let's say there is a word ABE, and let's say I need to convert it into ABC. What do I need to do? I just need to change this E into C. Let's say I make it into ABEE. So what do I need to do? I need to change this I need to change this C into E and add another E. So any word can be transformed into another word with a certain process. There can be insertions or deletions and substitutions. Now that is exactly what this automata focuses on. So over here, let's look into what exactly is dimensions distance. So over here, it is the minimum number of single character edits that are needed to change one word into another. Say for an example, I need to convert kitten into sitting. Now over here, my kitten, the K, I'm going to convert it into S. The E over here is going to be converted into I. And then I'm going to insert a G in the end. So I can either do insertion, I can do substitution, I can do deletion. Here I'm doing three of those. So I'm going to tell my edit distance is 3. So this is one way in which I can convert anything into anything. Okay. Then now let's just take another example. Let us say I have the word, I need to correctly type the word salad, and salad is going to be accepted. Now this one automaton accepts for k equal to 2, which means that it can accept for the distance of 0, 1 and 2. Now what exactly is happening over here? This seems to be very confusing, right? So over here, this 0 stands for the total number of operations that we have made to convert this into a proper acceptable string. Similarly, this 0, this one basically means the number of characters that we have passed through. So say for an example, I have the word salad and I need to convert it into salad for it to be accepted. So first what I do, I start over here, which means I have passed 0 characters. There are 0 errors or 0 edits or whatever I've done. So I'm going to S, passed 1 character, 0 over here. Okay, now this is how if I keep going, then what is the purpose of this and this? So over here, the horizontal means there is perfect match. You don't need to change anything. Vertical basically means you need to do insertion. And over here, these diagonal lines, basically this epsilon stands for deletion and this one stands for insertion. Now as we go, let's see. I start with 0 hash 0, which is S. And then I start with 1 hash 0, which means I've crossed one word and there are 0 errors. Then I go for A is also there accepted. Then I go for L. L comes to this state where I've crossed 3 letters and no errors at all. Then now I have I, but I need A. So what I can do, I need to replace this I with an A. So what I'm going to do is I'm going to go over here. I'm going to go over here. So which means that I have replaced with A. So now I've come to this position where I'm going to say, okay, I have come to this position. I have replaced it with an A. And now I have made one edit and I have crossed 4 characters. Now I have crossed 4 characters and now my last letter is D. So we now finally come to the accept state, which is 5 hash 1. So now this basically helps us in converting one word into another using certain distance. So let's say k is equal to 2, this will be able to accept all things for k equal to 0, 1 and 2. So here also I can have another word, let's say SAAAAD. I need to delete this, change this to I. So in such a case, I have made 2 operations. So mine will finally end up getting accepted over here. Now, let's also see about the use of this finite automators in natural language processing. So what exactly is natural language processing? Natural language processing is a field of artificial intelligence that will enable computers to interpret and understand the human language. So at the core, what this AI is particularly trying to do is it's trying to find patterns. Now, whatever sentence we give, it will try to break down. There are various methods that it does it with, like tokenization, speech tagging, name entity recognition, and many more. Now, what this will do is it will help the search engine understand the user's query better. Now, where exactly is this finite automata used in NLP? Now we know tokenization. What is tokenization? Say for an example, if I have a big sentence, I don't have a bat, then this will basically help us in splitting this have a bat. Say for an example, like finite automators can be used to match white space, punctuation, or regular patterns. We know, right? We can have certain states like this and then finally find out wherever the space is. If there are white spaces, we know that we have the certain words. We can break down a sentence into words depending upon white spaces, punctuation, lines, and such, right? So in that cases, finite automata can be used. Then we also use lexical analysis where we had different states pre-trained already based on the words that are there in the dictionary, and depending upon that, we can check whether the token is a number or word, similar to what compilers do. Then we had spelling corrections that I already showed you before. There are certain edit distance, and depending upon that, it can suggest you the corrections. Depending upon what you type, depending upon how wrong it is, it can tell you how what and all are the possible words, what and all. If you see, it's basically telling you by saying that within this edit distance, it can tell you, okay, you're typing this, that word does not exist, but if you edit it, these are the certain words that are also available, is what it is trying to say. Then we have something called as morphological analysis. So here what we're trying to do is if there is a big word, then we will strip and change that big word into a small word. So say for an example, it is called as running. So this running is basically broken down and called and transformed by the finite automata into run. Then we also have something called named entity recognition models, which will basically are particularly trained in recognizing certain names or patterns. Like say for an example, you have something called doctor name. It can help you to detect that particular name, or there can be certain formats for dates and all these things, and they are matched using this automata. Then we also have grammar checking. Like simple grammars can be represented, not very complex, but simple grammars can be represented by these finite automatas, and they can also help in detecting those. Now, we come into something very important and very interesting also, a hidden Markov model. So, say for an example, I am typing something and we said that depending upon the keyword matching, depending upon what and all are present, the server is going to, the search engine is going to list out all the most relevant searches. But now we have something called as a hidden Markov model. So, what exactly is a hidden Markov model? It is a statistical model where the system being modeled is assumed to be in a Markov process with a hidden state. So what exactly is that? So what is the hidden state in this case? So imagine you have to, your goal is to find out what weather it is, but you are not given what the weather is directly. So over here, your weather is going to be your hidden state. So you have to find out whether it's sunny or whether it's rainy. So, but then all you can see is whether people are wearing t-shirts, whether people are wearing umbrellas, and people are wearing jackets. You cannot find out what the weather is. The windows are closed, but you can see people walking. You can say, okay, some people are wearing t-shirts, some people are wearing umbrellas, some people are wearing jackets. By observing what someone wears, you try to infer the weather. Say, for an example, if someone is carrying an umbrella, we can say that it is rainy. If someone is wearing a jacket, we can say that, okay, fine, it might be a little bit cold. And t-shirt, we can say we can relate it to sunny. Okay, this seems to be interesting. How exactly is it used in finite automata and especially in search engines? Now, let's say I type, a user gives a query, cheap flights to Paris in July. So what I'm going to do is my a model will give you a tag for each word. So for an example, this cheap will be assigned a tag price modifier. Flights will be assigned a tag travel time. Paris will be assigned a tag destination, and July will be assigned a tag time. Now we have this something called tag sequence. We have price modifier, travel type, destination, and time. Now, what our finite automata will do? Basically, now we are allowing the search engine to understand what the user is trying to, the query that the user has given. Now we can basically identify it as a travel query, something they are trying to find out depending upon whether it's a travel query or not. So now we have a finite automata and we match the tag sequence. Now we also know that there is a match that is found. The finite automata finally helps us in matching it. Now, what it will do is it will give you the most relevant searches. Now trigger flight search logic with the filters like price, depending upon the price they're giving, depending upon the travel type they're giving, depending upon the destination they're giving, and depending upon the time they're giving, it will be able to filter out all these things. So HMM model is basically for giving you all the stacks, and finite automata is helping you to match the stack sequences and then filtering out all the most relevant search results. And these are few of the things that are two of the important components that are there in a search engine. And finite automators do play a very important part in a search engine. Thank you.